Hello friends, good morning. Welcome to our chemistry class. Today we are going to discuss about some of the most important concepts in coordination compounds. Okay friends, let us start. See, first of all, I want to tell you the order to remember the means to distinguish strong field ligand and weak field ligand. Okay, here I have written as SFL, that is strong field ligands. Okay, here it is the weak field ligand. Okay, first you have to remember this order friends. It is very important to remember this because if we have idea about the strong field ligands and weak field ligands, it is very easy for us to find the hybridization in coordination compounds. Okay friends, let us see the order. Okay, first this is the carbonyl group. Okay, carbonyl group, and this is the cyanide group. Okay, nitrite, en means ethylene diamine. Okay, ethylene diamine, and this is the ammonia. Okay, all these comes under strong field ligands. Okay, already we know that strong field ligands have low spin complex, and here the spin is paired. Okay, spin is paired means while finding the hybridization for the coordination compounds, I will explain you all these things. Okay, see, first try to remember these. Okay, these means like carbonyl, cyanide, nitrite, ethylene diamine, ammonia. Okay, these comes under strong field ligands. Okay, one more point I want to tell you friends, that is strong field ligand do not follow the regular Hund's rule. Okay, this is the thing which we have to remember. Okay, see, strong field ligands, in the strong field ligands the spin is paired. Okay, spin is paired, and here it undergoes D2sp3 hybridization. Okay, and next see this pyridine, pyridine, water, thiocyanate, fluorine, chlorine, bromine, iodine. Okay, all these comes under weak field ligands. Okay, weak field ligands means these have the high spin, and here the spin is free means these do not undergo pairing, so here the spin is free. Okay, and these weak field ligands undergoes sp3d2 hybridization. Okay, and see, and here means by using these I wanna tell you how to find the hybridization in the coordination compounds. Okay friends, let us see. Okay, see, here it is the coordination compounds. Okay, here the central metal atom is what? Cobalt. Okay, see, cobalt, what is the atomic number of cobalt friends? See, for iron the atomic number is 26 na? For cobalt it is 27. Okay, 27. Let us try to write the electronic configuration for this cobalt. Okay, see, argon means what? 18. Next, 3d4s2. Okay, argon is 18 na? 18 plus 2 20, and next we have to add 7. Okay, now check the electronic configuration. Okay, the atomic number of cobalt is 27. Argon, the atomic number of argon is 18. 18 plus 2 what? 20. 20 plus 7 27. Okay, now the electronic configuration is okay friends. Next, see, here the cobalt undergoes +3 oxidation state. Okay, see, cobalt in +3 oxidation state. That means here we have to remove 3 electrons. Okay, 2 electrons should be removed from this s orbital and 1 electron should be removed from this d orbital. Okay, now it can be written like this. Okay, argon, okay, 3d means see, here we are removing 3 electrons because here the cobalt is in +3 oxidation state, so here we will get 3d6, 4s 0. Okay, now see, now we have to write the orbitals like this. Okay, d 1 2 3 4 5. Okay, 4s, it's a 0, right? Next, 4p. Yeah, after 4s we will get 4p friends. Okay, and here also we don't have any electrons now, that's why we should write 0. Okay, p means here it will be like this. Yeah, see, in the d orbital 6 electrons are present, that means we had to write like this. Okay, 1 2 3 4, 5, 6. Okay, and see, s and p orbitals are empty, so it should be left like this only. Okay, next, see, here the ammonia is either strong field ligand or weak field ligand. Let us check here. Okay, see, here the ammonia is strong field ligand. Okay, strong field ligand means what? Spin pairing occurs. Okay, this point we have to remember. Okay, strong field ligand means spin pairing occurs. Spin pairing in the sense, see, here the electrons here means they will pair up like this. Okay, now it can be written like this. Okay, 1 2 3 1 2 3 4 5. Okay, see, pairing means, see, this one comes to here, so here we had to write the two electrons like this, and here also the same thing. Okay, now count the number of electrons: 1 2 3 4 5 6. Okay, it's fine. Yeah, next, this is p, sorry, this is s, and this is p. Okay, see, and see, now we had to look at this ammonia. Okay, here 6 ammonias are present. 6 ammonias are present. That means here, see, this ammonia is what? Strong field ligand. Okay, and see, we know that ligands have the ability to donate. Okay, ligands have the ability to donate. So here 6 ammonias are present. That's why they donate to 6 orbitals. That means, see, 1 2 3 4 5 6. Okay, and this is our hybridization, friends. We know that this is the d orbital, this is the s orbital, and this is the p orbitals. We had to look at the orbitals where the electrons are getting contributed by the ligands. Okay, here the ammonia has contributed its electrons to 2 orbitals of d, okay, and s and p. So here the hybridization is d2sp3. Okay, d2sp3. So here this is our hybridization. Now let us check this, friends. Okay, see, this is the ammonia. Okay, ammonia is the strong field ligand, and here it undergoes d2sp3 hybridization. Okay, and see, here lone pair of electrons are absent, na? That means here it is what? Diamagnetic. Okay, diamagnetic. And as the lone pair of electrons are absent, we can also say like it is colorless. Okay, so based on the hybridization, see, we are able to tell these. Okay, next, I hope you understood this, friends. Nothing, friends, just I want to tell you once again. Okay, let's have a quick look at this. Okay, first we have to look at the central metal atom. So here the central metal atom is what? Cobalt. So first of all we have to write the electronic configuration. Okay, this is the electronic configuration, and here the cobalt is in +3 oxidation state. So here 3 electrons should be removed. Okay, from S we are able to remove 2 electrons, and 1 electron should be removed from the d orbital. So it should be like this. Okay, 3d6, 4s0, 4p0. Okay, as this ammonia is the strong field ligand, spin pairing occurs. So the spin pairing occurs like this. Okay, so that all the electrons get adjusted in these 3 orbitals. Okay, and these remains empty. Okay, and as we have 6 ligands. Okay, we know that the ligands have the tendency to donate electrons. So as 6 electrons are donated to 6 orbitals. So 1 2 3 4 5 6. So this is our hybridization. So d2sp3 is our hybridization, and here lone pair of electrons are absent now. That's why it is diamagnetic, and this is colorless. Okay, now let us look into another example, friends. Okay, see, here we have the zinc. Okay, the atomic number of zinc is what, friends? I think 30. Yeah, yes. Now let us try to write the electronic configuration of zinc, friends. Okay, argon 3d4s2. Okay, argon means 18. Okay, 18 plus 2 20, 20 plus 10 30. Okay, this is the electronic configuration of the zinc. Okay, here the zinc is in +2 oxidation state. Okay, that means here we had to remove 2 electrons from the s orbital. Okay, so it can be written like this: argon 3d10 4s0. Okay, so our electronic configuration is like this. Okay, argon 3d10 4s0. Okay, Now let us write the orbitals in this manner to find the hybridization of zinc. Okay, 3d, 4s, okay, and 4p. See, d means 5 orbitals are present. 1, 2, 3, 4, 5. Okay, and this is the 4s and this is a 4p. Okay, see here in this d, 10 orbit means 10 electrons are present, so d10. Okay, and 4s is empty, so 4s 0. Of course 4p is also empty, so 4p 0. Now let us let us put the electrons in this. So 10 electrons means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so d10. Okay, now let us look at this ligand. Okay, here we have the bromine. Okay, bromine is what? It is weak field ligand. Yeah, see, let us see. Yeah, here we have the bromine and this is the weak field ligand. Okay, yeah, yes, see, bromine is the weak field ligand, and first here we had to look at the number of ligands. Okay, here we have the 4 ligands. Okay, that means see 4 orbitals should be filled. Okay, that means 1. See here the d orbital is completely filled now, so that's why we had to look at the adjacent orbitals. Okay, see here the bromine, this is the weak field ligand, so 4 orbitals should be filled. 1, 2, 3, 4. Okay, yeah. Now see, of course here the bromine is the weak field ligand. Okay, weak field ligand means what? See, weak field ligand means spin is free, so pairing is not possible. Okay, of course here pairing is not possible because already here the electrons are paired up. Okay, now our hybridization is what? Here S and 3 p orbitals are filled by the ligands. So here our hybridization is sp3. So it is sp3 hybridization. Okay, and here the lone pair of electrons are absent, that means here it is dia, and of course here it is colorless. Okay, hope you understood this. Yes, now let us take the last example for today's class, friends. Okay, here we have the manganese. Okay, the atomic number of manganese is 25. Okay, now we had to write the electronic configuration for the manganese. Okay, argon. Okay, argon is 18 now. Yes, argon 3d 4s2. Okay, argon means 18, means the electronic configuration of argon is 18. So 18 plus 2 20 plus 5. So this is the electronic configuration of the manganese. Okay, here the manganese exists in plus 2 oxidation state. So manganese plus 2. So here the 2 electrons should be removed from the outermost orbit. So here the 2 electrons should be removed from this s orbital. So here we will get 4 as 0. Okay, and of course 4p is also 0. Yeah, next, yeah, try to draw the orbitals for this. Okay, 1, 2, 3, 4, 5. That means here we have the d orbitals. Okay, means 5 orbitals. 1, 2, 3, 4, 5. Okay, next 4s and 4p. Yes, this is S, this is P. Okay, see, friends, this chlorine is the weak field ligand. Okay, chlorine is the weak field ligand. Okay, see, first let us fill these electrons in the d orbital. Okay, in the d orbitals 5 electrons are present now. So 1, 2, 3, 4, 5. Okay, s and p orbitals are empty, so it should be left like this. Okay, see, in the d 5 orbitals are filled. Okay, now this is very important to remember, friends. Okay, here pairing should not occur because this is the weak field ligand. Okay, already I told this point. Okay, see, this chlorine is the weak field ligand. Okay, in case of weak field ligands, okay, pairing do not occur. Okay, let me tell you that. Okay, see, in case of weak field ligand, spin is free. Okay, spin is free, that means pairing does not occur. So it should not be paid, friends. It should be like this only. Okay, it should not be paid. Yeah, I think you understood this, okay? Means in the last example, I have, means in case of strong field ligand, I have paired up like this, okay? But here in this case, as this is the weak field ligand, pairing should not occur. So that it should be left as like it, okay? Next, see. Here the chlorine is present, okay? How many chlorines are present, friends? Yeah, 4 chlorines. That means 4 ligands are present. So that what is the tendency, means what is the nature of the ligand? Its nature is just to donate the electrons now, okay? As here the 4 ligands are present, it is able to contribute its electrons to 4 orbitals, okay? That means here 4 ligands are present now. So 1 2 3 4, okay? And now this is our hybridization, that is sp3 hybridization, okay? See friends, here lone pair of electrons are present now, that means here it is paramagnetic, okay? So this is the paramagnetic sp3 hybridized, and it should be colored because it is paramagnetic now, so it is colored. Yeah, next, see friends, these are the very important friends, okay? That means without following all this, we are able to tell just by looking at the coordination complexes. So if we know these 3 points, then it will be very easy for you to find the hybridization, okay? See, note friends, all platinum plus 2, palladium plus 2 tetracoordinated complexes are square planar and they undergo DsP2 hybridization. Okay friends, nothing friends, just whenever we find a coordination complex, that too tetracoordinated complex, okay, this is the tetracoordinated complex, right? Yes, if in this tetracoordinated complex, if the platinum or palladium is existent plus 2 oxidation state blindly, we had to, okay, means we come to know that this platinum undergoes DsP2 hybridization and it is square planar, okay? You should remember this friends. First look at the coordination complex, if that is tetracoordinated complex and the central metal atom is platinum or palladium in plus 2 oxidation state, okay, that undergoes DsP2 hybridization and square planar, okay? Next note friends, okay, all zinc plus 2 tetracoordinated complexes are tetrahedral, okay? See, tetracoordinated means what? Just the ligand should be 4 in number, that is tetracoordinated complex, okay? If in that tetracoordinated complex, if zinc is present in plus 2 oxidation state, that is said to be tetrahedral and they undergoes sp3 hybridization, okay? Next, last point, okay, all nickel plus 2 octahedral, OH means octahedral, okay, all nickel plus 2 octahedral complexes are high spin and paramagnetic, okay? See, this is the octahedral complex because here we have the 6 ligands, okay? Here also we have the 6 ligands, okay? That means these two are octahedral complexes. And see, nickel plus 2, so here the nickel existed plus 2 oxidation state, here also, okay, nickel existent plus 2 oxidation state, okay? Nickel plus 2 octahedral complexes are high spin paramagnetic and they undergoes sp3 d2 hybridization, okay? High spin means what? See here, okay, high spin means that is weak field ligand and there the spin is free, so they undergoes the sp3 d2 hybridization, okay? Hope you understood this concept friends. Thank you.